Hello, in this video we're going to deal with the Nobel Prize in Physiology or Medicine for the year 1911, awarded to Allvar Gullstrand for his work on the dioptrics of the eye. You see a general view of the eye with its different parts. If you want to study it, pause the video, or guys go to the link. Here a little more information about why Gullstrand received the prize. It's coming from the original Nobel Prize site, as you can see here in the link. Our vision is based on the eyes breaking up light from outside world and converting it to an image at the back of the eye. From here, photosensitive retinal cells convert light into nerve impulses that eventually become visual images. Calculating the pathways of light through the eyes and how an image is created is very complicated because the eye consists of different layers that refract light to different degrees. Moreover, the lens also changes shape. However, Allvar Gullstrand succeeded in doing just that in the 1890s using advanced mathematics. There's some biographical information also come from the official Nobel site and summarized by me. After holding various appointments as a doctor and a lecturer and serving on the Swedish medical board, he was appointed, he is of course Gullstrand, the first professor of ophthalmology, difficult word, at Uppsala University. In 1894, he occupied his post until 1913. As from 1914 onwards, he held a personal professorship in physical and physiological optics at Uppsala University. He was appointed emeritus professor in 1927. He was entirely self-taught in the fields covering his most important work, which is geometric and physiological optics. The basis of the science he developed was laid in 1890 in his thesis Bijdrage till astigmatism theory, contribution to the theory of astigmatism. The complete proof of his theory is found in the following three works: Allgemeine Theorie der monochromatischen Aberrationen und ihre nächsten Ergebnisse für die Ophthalmologie, oftewel, this means General Theory of Monochromatic Aberrations and their immediate significance for ophthalmology from 1900, which received awards from the Swedish Royal Academy of Science and the Swedish Medical Association. Then second, die reële optische Abbildung, the true optical image from 1906, and die optische Abbildung in heterogenen Medium und die Dioptrik der Kristallinse der Menschen, the optical image in the heterogeneous media and the dioptrics of the human crystalline lens. From 1908, which was awarded the centenary gold medal of the Swedish Medical Association. The results are combining in the work Tatsachen und Fiktionen in der Lehre von der optischen Abbildung, Facts and Fictions in the Theory of the Optical Image, from 1907, and Handbuch der Physiologischen Optik, Handbook of Physiological Optics, by H. von Helmholtz, 3rd edition, volume 1, 1909, and Einführung in die Methoden der Dioptrik der Augen des Menschen, Introduction to the Method of the Dioptrics of the Human Eyes, from 1911. Of his other works, the following received awards: Objektive Differentialdiagnostik und photographische Abbildung von Augenmuskelenungen, the objective differential diagnostics and physiological evaluation of the disabilities of the eye muscles, from 1902. Photographische ophthalmometrische und klinische Untersuchungen über die Hornhautrefraktion, photographic ophthalmometric and clinical investigation of corneal refraction, from 1896. Die Farbe der Macula Centralis Retinae, the pigments of the central macula of the retina, from 1905. The first two received awards from the Swedish Medical Association, and the latter received the Björken Prize of the Uppsala Faculty of Medicine. Gullstrand devoted himself mainly to the calculations and methods for achieving a more suitable form of the refracted surfaces in optical instrument and to investigations of the optical system laws of higher order. A result of the former is a record which is kept in the Uppsala University Library, which relates to the calculations for optical systems, inter alia optical systems with the appropriate non-spherical surface, and the publication über asphärische Flächen in optischen Instrumenten on aspheric surfaces in optical instruments from 1919. As a result of the latter, we may mention the publications Das Allgemeine Optische Abbildungssystem, the General Optical Image System from 1915, and the Optische Systemgesetze zweiter und dritter Ordnung, Laws of the Optical Systems of the Second and Third Order from 1924. He gave the last summary of his optical experiments in Einiges über optische Bildung, some aspect of optical images from 1926. His method of focal illumination, particularly by means of the slit lamp from 1911, have acquired the greatest importance to the practical ophthalmologist. His reflex-free optical mesoscope from 1911 is a valuable instrument to the ophthalmological diagnostication. This is summarized by me from the official Nobel Prize site. If you want to read complete information, follow this link. Here again see a picture which in general shows that if an eye is looking at a point which is far away, the lens is more or less flat, and if the eye is looking at the point which is nearer, the lens becomes thicker. Here you see the same object near, lens is flat, object far away, lens is thick, object far away, lens is flat. Then a award ceremony speech by Count Mörner, summarized by me again. Research into optical systems and the images obtained through them goes back to the very distant past. One can name many illustrious physics and mathematicians who studied these problems and have tried to formulate a solution. The belief was widespread at the time, and is perhaps still held in some quarters, that the theoretical study of these matters has been completed and that nothing remains to be added to it. This belief can particularly be explained by the fact that the technique for the establishment of this optical system has had very important advances, particularly in the past decades. It emerges, however, that the theory of optical image formation was in several respects incomplete, in some others erroneous. In man-made optical instruments, the refracting media consists of homogeneous substances, and usually a regular, predetermined shape is given to the refracting surfaces. To explain the image thus obtained has in itself far from easy. If we now consider the eye, we are faced with an optical system of particularly complex structure and with conditions of refraction of equal intricacy. This is due primarily to the lens in the eye, because its refractive power varies considerably from layer to layer, and also because in order to see at different distances, it changes its shapes and refractive capacity. From the theory of normal and abnormal conditions of the eye, it is naturally of paramount importance to elucidate the problems of light reflection and visual image formations in the eye, since the physical operation of the eye as an optical instrument is a necessary condition for its operation as a sense organ. The clarity of the image produced on the retina is a factor which determines the power of vision. Therefore, the study of optical image formation in the eye is an important branch of physiological optics as well as ophthalmology, and has occupied many famous scientists. It's fitting to mention the scientists who did a complete contribution in this field before Gullstrand, namely Hermann von Helmholtz, whose famous name will still be remembered. The pioneered work of von Helmholtz threw so much light on the subject of refraction and image formation in the eye that it seems most unlikely that after him work could be produced of such revolutionary impact on the science as that of Gullstrand. The scope of this work and its very nature as such as to prevent me from reporting in detail on it, I must renounce the idea of describing the preparatory experiments performed as well as the practical application resulting from them. I wish, however, to be permitted to give a brief outline of the development and importance of this work. It started some 20 years ago. As an ophthalmologist, Gullstrand wanted to answer certain questions relating to light reflection and the optical images formed in the eye. He soon realized that much work still had to be done to formulate the general laws of optical image formation. The complete solution of this problem became the first task of Gullstrand in his work towards his ultimate goal. He has completed this task. He has transformed the theory of optical image formation and has formulated the fundamental equation from which there are derived the hitherto unknown laws of optical image formation. He thus gained a reliable starting point for a fruitful continuation of his study of the eye. Indeed, some difficult aspects of this problem still remains to be solved. Refraction in the eye especially presented difficulties which had previously been insoluble. It is difficult to say at least to charge the passage of light through a medium whose refracted index varies from layer to layer. Furthermore, little was known about the laws which govern the changes in the shape of the lens to enable clear images to be formed of objects placed at different ranges, or of the influence which changes in curvature have on the refractive power of the lens, the importance of the diaphragm of the eye, and several other details were imperfectly known or inaccurately interpreted. Thanks to Gullstrand, the problem to which I have reflected have all been solved, and he has elucidated the formation of optical images in the eye and has incorporated in the general laws governing optical image formation, also established by him. Well, this is the summary of the award ceremony speech given to Gullstrand in 1911. If you want to read the complete speech, follow this link. Here you see some of the problems he was working on, in this case astigmatism. Here you see the original view, and you see that the horizontal and the vertical focus are also a bit blurred, and this is then the compromise. You see that the lens, which is generally seen as a homogeneous object, is in fact built in layers which all have a different composition, which makes, of course, the way the light travels more complicated than if it was a homogeneous body. That is one of the, I think, the most important contributions from Gullstrand to the understanding of how the eye lens work. Next week we will go into the, I would say, rather complicated Nobel Prize lecture by Gullstrand. It's very mathematic, and it is said that for most of his colleagues his work was too complicated and too mathematical, but he'll do an attempt to summarize his, as I said, quite complicated speech in the next video. For now, thank you for watching, and maybe I'll see you next week or another time on this channel in which we will all deal with Nobel Prizes.